Hello everyone! And yes, it has been a while. It's been a busy start to the summer, had a lot of things going on, but I do think I will have more time from now on for math content. So let's go ahead and get right back into it with this fun little sum right here. So you might be thinking, what on earth is this? Because it looks sort of like a zeta function, right? With this whole s right here. And it sort of looks like the zeta function again with, this 2k plus 1 in the denominator, but what on earth is this k doing here? And that's what we're going to figure out today. We're going to derive a formula for this right here in terms of the zeta function. So let's get to it. The first thing we're going to consider is not the nth case for this. What we're actually going to do is consider the 0th case, and then the first case, and so on and so forth, and do some induction, and then get our formula that way. So let's go ahead and consider, really just this expression right here. We're not going to worry about the sum at the moment. That'll be rather simple later. Working with this algebraically, what is the 0th case? Well, if we have n equals 0, well, that's actually incredibly simple. That's just going to be, make a little table. This is just 1 over 2k plus 1 to the s. Okay, cool. What about n equals 1? Well, in that case, we have k over 2k plus 1 all to the s. But this right here, we can simplify a bit. Let's multiply the top and bottom by 2, and in the numerator, add 1 and also subtract 1. So what this means is that this expression is now 2k plus 1 minus 1 over 2k plus 1 to the s. Okay, well, we obviously see that this term right here is going to cancel with one of the 2k plus 1 2k+1s in the denominator. So if we go ahead and evaluate that, we're just going to have, there should be a 2 in the denominator right there, 1/2 times everything, and then just 1 over 2k plus 1 to the s minus 1, and then just minus 1 over 2k plus 1 to the s. It's kind of hard to see a pattern this early though. So let's go ahead and consider the case n equals 2. And from there, we might be able to see some sort of pattern emerge. So obviously it's just going to be, k squared and over 2k plus 1 to the s. But what we can really do with that is consider that as k times k over 2k plus 1 to the s. So really we can just say it's k and then times all of this right here. So we can just say it's k on 2 and then times 1 over 2k plus 1 to the s minus 1 minus 1 over 2k plus 1 to the s. Okay, let's go ahead and split these terms up further because we have this k and we have this right here. And we know that if we have a k over 2k plus 1 to some s, it doesn't really matter if that's an s or s minus 1, we're just going to get this formula right here. So let's go ahead and just evaluate that. So with the first term, we're just going to have, 1/2 out front, obviously. And then we're going to have 1 over 2k plus 1 to the s minus 2, because we're considering this s minus 1 term, right? So all the s's are just going to be, minus 1. And then we're going to have just minus 1 over 2k to 2k plus 1, obviously, and then to the s minus 1. And then we're going to have minus, exactly what this is right here. So minus 1/2, and then 1 over 2k plus 1 to the s minus 1, and then minus 1 over 2k plus 1 to the s. And although empirically there might not be a ton to support this idea, certainly whenever you compute these, you're kind of getting a vibe of something binomial going on. Because what you see is that whenever you increase n by 1, each term is going to spit out an additional 2 terms. But some of those terms aren't going to be completely independent of each other, right? Like these two are the ones that resulted from these terms right here. But these right here are, they're both 1 over 2k to the s minus 1, so we can combine those. So let me go ahead and simplify this, and I think this might further show the point, factoring out the 1/2 from the inside of the parentheses, we have a fourth, and then we're just going to have 1 over 2k plus 1 to the s minus 2, and then minus 2 over 2k plus 1 to the s minus 1, and then plus 1 over 2k plus 1 to the s. And you'll see with this pattern, with these terms being both 2k plus 1 to the s minus 1, but they came from different terms to begin with, the fact that they end up the same kind of does point to something binomial going on. And we do actually see that reflected right here, because we have binomial coefficients. It might be a little bit silly to say that, but if we want to generalize this further, then it's certainly necessary. Here in the 0th case, well, the 0th, 0 choose 0, it's just 1, so that's a 1 there. In the first case, so or the second case, n equals 1, we end up with 2 1s, but that's also fits a binomial case. And then we also have this 1 to 1 here in the n equals 2 case. So this does point to some sort of binomial pattern going on. But to really hammer this home, let's go ahead and consider the case n equals 3. So n equals 3. Now I'm not going to go ahead and compute this because I don't want to spend half this video on just algebra alone. So as a quick spoiler, you can compute this on your own to make sure it's right. But this right here is just going to be, and here you can really see the binomial pattern shine. So let's go ahead and try to write a general rule and then prove it by induction. So let's go ahead and just look at each expression kind of bit by bit and try to pattern match into a more general pattern. So let's go ahead and start actually with the coefficients in front of the whole expression, right? So in this first one, or actually in this last one right here, we have 1/8, then we have a fourth, and then a half, or sorry, the half is actually right here. So we have an eighth, a fourth, a half, and then the first one is obviously just 1. So it seems quite clear that the general rule right here, at least for the coefficient out front, is just going to be some 2 to the minus n. Let's go ahead and consider what's inside the parentheses. So we have the sum from, let's just call it sum j equals 0 all the way up to n. The reason for that being that we have n plus terms in each expression. So for n equals 3, you will notice we have 4 terms. For n equals 2, we have 3 terms, and so on and so forth, right? Obviously, we see the binomial coefficients in front of each, right? So, we have this 1, 3, 3, 1, right? So we obviously have the binomial coefficients. So it's just going to be n, and then just choose j. Simple enough. You'll also notice that they're alternating, so you can just throw in a -1 to the j. And then lastly, what we're going to need is, the actual part of the expression that's arguably most important, the one with the 2k plus 1 in the denominator. But that right there seems simple enough, because in the way we've been writing this, we just start with this s minus n, and then we just sum all the way up to just s. So really, it's just going to be 1 over 2k plus 1 to the s minus n and then plus j. Now this right here seems plausible, but let's go ahead and actually try to prove it. So let's go ahead and consider what we expect to get whenever we consider the n plus 1th term. Here we go again. To actually prove this by induction, we first need to figure out what the next term in this sequence should look like. So instead of starting with the formula we just derived, what we're going to do is consider k to the n plus 1 over 2k plus 1 to the s. Now we can simply rewrite this as k to the n times k over 2k plus 1 to the s. And now we can just simply rewrite this as, well, k to the n on 2, and then just times 1 over 2k plus 1 to the s minus 1, and then just minus 1 over 2k plus 1 to the s. So when we multiply this expression right here by k, we should expect to get something that looks like this. So let's go ahead and do that, making this just into a k. What exactly do we get? Well, we can go ahead and actually split up this term right here, like we just did with this inner term. This means that this right here is going to just be equal to this 1/2 and then 1 over 2k plus 1, and then to the s minus 1. And in this case, we have s minus 1 minus n plus j. A bit of a mouthful, but gets the job done still. And then we're also just going to have minus this 1 over 2k plus 1 to the s as in here, but it's just going to be an s minus n plus j instead. Now that we have this, let's go ahead and expand this out with the sum. Distributing everything, this right here is what we're left with. It'd be awfully nice if we would be able to consolidate some of these terms. Ideally, what we would get is a single term with a single 1 over 2k plus 1. So let's go ahead and try to consolidate some of this. And the way we're going to do that at first is actually just going to be by reindexing this sum right here. You'll see that we have a j and then minus 1 right here. So we're just going to reindex. From this, we get the sum from j equals -1 all the way up to n minus 1. And then we have n choose j plus 1. And then -1 to the j plus 1 or minus 1. It's -1, doesn't awfully matter, but it's plus 1. Then we have 1 over 2k, and then to the s 2k plus 1 to the s minus n plus j. Now, it would be awfully nice if we were able to factor out this 1 over 2k plus 1 to the s minus n plus j term right here. But there's an issue. Sort of, not really. The sum right here goes from j equals -1 all the way up to n minus 1. But this sum right that's going over this term right here, it's really this one right here, goes from j equals 0 all the way up to n. So are we able to add those two? And the answer normally to that would be no, you aren't able to. But in this case, you actually are. And the reason for that is because, take this term right here. N choose -1, in this case, it's just going to be negative. So whenever we evaluate the sum from j equals -1 all the way up to n, this term right here is just going to be 0 and not actually contribute anything. And likewise, you'll see that we have a j plus 1 right here. So if we evaluate the sum at n, the term that results is just going to be 0. So in reality, we can rewrite this whole thing in simplifying the 2 out front, so 2 to the minus n minus 1. We can rewrite this whole thing as a sum from j equals -1 all the way up to n of, well, we can go ahead and factor out what we wanted to factor out, this 1 over 2k, and then plus 1 to the s minus n plus j, and then times this n choose j plus 1 times -1 to the j plus 1, and then minus n choose j, and then -1 to the j. Now we can actually go ahead and simplify this further. I haven't closed the parentheses for a reason. We see that this right here is negative, right? So really what we can do is just make this a plus and add 1 to the exponent here, but then we can also just factor out that -1 term. So I just want to go ahead and do that right now. We can just throw this -1 to the j plus 1 term to the outside. And this right here is our expression now. And you'll notice that this right here is actually sort of special. This is one of the properties of the binomial coefficients. When you add them like this specifically, what you end up getting actually is n plus 1 choose j. This is a fun proof, but I'm not going to do it in this video. I think it'd make a good short or something. But at any rate, scrolling on down. Putting this all together, we have 2 to the minus n plus 1. You can write it like that, because we are doing induction, you know. Now we have the sum from j equals 0 to n plus 1, because we can reindex. And with this coefficient out front, we have n plus 1. I do apologize, there should be a plus 1 there on the binomial term. Apologies. But what this makes us now is just a nice little j. And then we just have our -1 and then to the j. And then we have our 1 over 2k plus 1 to the s minus n and then plus j minus 1. But we can see that this -1 and this -n term can be grouped to where it's 1 over 2k plus 1 and then plus j minus n plus 1. So we can go ahead and write it like that. And we see that this indeed, if we go ahead and look back at our original expression, this is what we get when we change n to n plus 1. So this is our original expression right here. Obviously this right here was a 1, but I think you get the idea. So if we change an n to an n plus 1 in that expression, we end up with the next term in our sequence if we multiply it by k. Thus, this is proven by induction. Now, the base case is relatively obvious. So scrolling up here, I mean, just plug in n equals 0, you end up getting, let's see, 1, and then 1, and then 1, and then just 1 over 2k plus 1 to the s. So base case is satisfied. So let's go ahead and actually evaluate this sum. Swapping the order of the sums, what we see is that we end up with just this expression right here, and it becomes a matter of evaluating this right here. But this isn't an awful expression to evaluate, because, as just a side note, say we have the sum from k equals 1 to infinity of 1 over k to some alpha. That right there we can split up into the sum of all even k and the sum of all odd k. So we can say this is the sum from k equals 1 to infinity of 1 over 2k all to the alpha, and then just plus the sum from k equals 0 to infinity of 1 over 2k plus 1 to the alpha. The reason why this sum is starting from 0 is that we do want to include 1 in the expression, right? So although it might not look awfully pretty, it does work. So to actually find the value of this right here, which is more or less what we have above, we can just go ahead and subtract this right here from both sides, and factoring out a 1 over k to the alpha, what we end up getting is just 1 minus 2 to the minus alpha, and then times, well, the sum from k equals 1 to infinity of k to the minus alpha, but that right there is just going to be zeta of alpha. So that right there is what the sum is equal to. So using this quick little formula, we can actually just evaluate this sum right here. So this right here is equal to 1 minus 2 to the n minus j minus s, and then just times zeta of s minus n plus j. So to write it all out succinctly, so we get a nice little answer, the formula for the sum is going to be 2 to the minus n times the sum from j equals 0 all the way up to n of negative 1 to the j, and then n choose j of, and then times 1 minus 2 to the n minus j minus s, and then just times zeta of s minus n plus j. And that right there, ladies and gentlemen, is just going to be our answer for today. I hope you all enjoyed this video. There will be more math content coming soon.